So when it comes to the basic mechanics, right, we talked about two things, statics and dynamics, right? Statics is something, an object when it is rest, and studying of objects in motion is called dynamics, right? But the key thing I want you to take away is it all depends on the frame of reference. This is very important, right? So an object that you consider to be at rest can be actually at motion depending on the frame of reference that you're looking at, and vice versa, right? So the frame of reference from which you are observing or studying the object actually ends up determining if it is at rest or is it at motion. Okay. The next thing is, when it comes to stress, hopefully everybody is familiar that stress is nothing but force over area, right? So any force or any stress in a fluid can be decomposed into a tangential stress, which is also called as shear stress, and a normal stress, which in special cases will be equal to pressure, right? So this case in which the normal stress is equal to pressure is when the fluid is at rest. So if the fluid is at rest, the normal stress of a fluid is essentially just pressure. Another kind of finding or thing that goes along with the shear stress is, in a fluid there's not going to be any shear stress if the fluid is at rest. The fluid has to be at motion for that has to have any kind of shear stress. Okay. Now, after this, so next thing we went along was comparing a solid and fluid, right? So the main distinction scientifically made this on if an object is a solid or a fluid is the fact that if you apply a shear force, can the solid resist the shear force, right? Is there finite deformation? Versus in the case of fluid, there is no way to resist it completely. As a result, you have a continuous deformation as long as there's a force applied or shear force applied on the fluid, right? That is the main distinction. We looked at the problem of a liquid sandwiched between two concentric cylinders and the person rotating it. As long as he's rotating it, it will constantly deform, right? No matter how small of a force or how slowly he rotates it or how fast he rotates it, right? As a result, when you talk about solids, you're talking about strain, and while you're talking about fluids, you're talking about strain rate, because it's constantly deforming. You're talking about there's no way to specifically identify a change in length or change in angle, so you do it over a certain finite time. Hence, when it comes to solid, you have stress is proportional to strain, which you're familiar with, but in fluids, the stress is proportional to strain rate, right? So be mindful of this. You're proportional to strain rate and not the strain. Next, we compared the distinction between solid, liquids, and gas, right? So in solids, molecules are fixed or vibrate about its lattice locations. In liquids, it translates relatively freely, and in gas, it just wobbles around all over the place, right? So that's the most easiest and moves around all over. When it comes to solids, you have a very strong cohesive force. That is why the molecules are fixed to its location. In liquids, the interatomic forces are weaker than solids but still stronger than gases. So it still allows it to move around freely, but is still constrained in some sense. While as in gases, it has the weakest interatomic forces, right? This you're familiar with. The key thing I want you to take, which you might be less familiar with, about how these forces and this molecular structure determines the volume, right? So in solids, it's very obvious the volume is constant, while in gases, if you expose a gas in a container, it will always end up taking the shape of the container. So it will expand out to the point of the container or the volume provided by the container. But because the forces or interatomic forces in liquids is somewhere in between solid and gas, the volume is relatively constant, right? So we talked about a container or a bottle. If you just fill half of it, right, you'll see a volume that is half, right? It's not like gas where the water will just evaporate and fill up the whole, this liquid water will fill up this whole thing, right? So you might have some gas here, but the liquid will be confined to it, right? So it will all depend on the volume of liquid you have, right? So it takes somewhat of the shape of the container, but it all depends on the amount of liquid it has. It will not take the full shape of the container. So it's only relatively constant, right? So that's kind of the distinction that I want you to take away. Finally, we reviewed dimensions, which is essentially any physical quantity that can be measured. And when you're talking about dimension, you're not necessarily talking about the numerical values, right? The way to assign numerical values to a dimension is by adding units to it. Okay. We talked about basic idea of primary dimensions that is there. The one thing I emphasized is the fact that dimension homogeneity, that any quantity that is added up or subtracted has to have the same dimension, right? So if you have two, or you're equating two quantities, here A and then the product of B times C should have the same dimension. It cannot have different dimensions, right? So it would, if not, you're essentially saying you're adding apples and oranges, right? Which is not possible. Okay, next up we looked at accuracy and precision. Accuracy is essentially the closeness of the average reading to the true value, right? So if you have 20 points, how close this average is to the true value. So is the true value in the middle, then it's perfectly accurate, then the average of this is. But now if the true value was out the way here, this is not very accurate, right? While in the case of precision, it's talking about how distributed these points are, right? It does not matter how close it is to the final value. So if this is one of the distribution and the next distribution happens where everything is very close by to each other, this is more precise than this, right? So the closeness or the repeatability of an instrument. So if we take essentially the other way to look at it is the repeatability, right? If you make 10 measurements, it always gives you the same or very close to the same measurements, right? So that is the precision of an instrument. Okay. The last thing when we kind of talked about when it comes to precision is if you're adding or taking a product of two measurements or dividing it, right? The final result is only as precise as the least precise measurement that you made, right? So that is something to keep in mind and be mindful of. Last but not least, we talked about significant digits, and we said that the number of digits you use after the decimal place actually mentions the accuracy of the instrument or the measurement. So you cannot have an arbitrary number of digits after this because it is a misleading quantity, right? You are, instead of writing the time as or let's say the length as 3.50 meters, if you end up writing it as 3.501237 and keep on going, right, meters, you're saying that this is accurate to, let's say, 10 or 100 decimal places, which is probably going way below even the molecular length scales, right, which is not possible at all, right? So, or very hard, let's say, on all practical purposes, not possible, right? So you're misleading the person reading your report by providing so many extra digits, right? So everything in engineering that you do has a specific reason to it or logic behind it, right? So be mindful of the number of decimal places that you're using after it. If nothing is specified, you use 2 digits. That is kind of the engineering standard. If somehow it has been specified that you can measure up to three decimal places, or your accuracy of that instrument is this, then that is what you use, right? Okay, with that being said, we pretty much come to the end of this section. And as always, so this is just a basic, very top level overview, so we won't have any homeworks associated with this. If we'll have a quiz as a result on this topic, which I'll send out an email and post it on D2L, and it will be just conceptual based questions. Finally, if you have any questions or things are not clear, please feel free to reach out to me in office hours, or drop me an email and we can schedule an office hours. Okay. And that being said, thanks, and we are end of this lecture. So some of the last things in this first introductory section I want us to kind of emphasize or kind of go over is the distinction between accuracy and precision. Right? Accuracy and precision are often mixed up and used interchangeably, while in reality they are two very different concepts. Right? So when it comes to accuracy, or let's say accuracy or inaccuracy, in general, accuracy essentially of a set of measurements. So if you have multiple measurements taken by the same instrument, let's say, refers to how close of the average reading is to the true value, right? So if you have 10 measurements, if you average out that measurements, how close is it to the true or expected value, right? Whereas when you talk about precision, in general, you're talking about if you have a set of measurements you're taking, it refers to the fineness of the resolution or the repeatability of the instrument, right? And this is best explained by these two examples, right? So if you see here, right, you're hitting a target, right? All of these points or target or hits made are very close to each other, right? So all of them is in a very confined area. So you're making 10 shots and you're always hitting the same point, but you're always consistently hitting the wrong same point, right? So this is essentially precise, but it is not accurate, right? So you are constantly hitting you're easily are able to repeat. So that's kind of this point, right? The repeatability point. So you're consistent with all of your shots. You can always keep on repeating the same shot and make it at the same point. So your distribution of this is very confined. So this is very precise, but now you can see it is way off target, right? So this is precise but not accurate, right? So essentially you can say you're consistently hitting the wrong target, or you're consistently missing the target, right? You're consistent, but you're missing the target, right? Now on the flip side of it, you have this example B, right? Now you can see compared to this A, or your shots have been more distributed, right? So you're not consistent enough, right, compared to the example A. So you're hitting it, your distribution is more spread out, right? So you're not as repeatable, right? So if you're making 20 measurements, your measurements are more distributed or more off, right? But if you average out these measurements, you see that you are much closer to the target, right? So this set of measurements is more accurate but not as precise, right? So that is kind of the main distinction between accuracy and precision. So anytime you're doing an experiment, any kind of measurements you're doing, or any kind of simulation you're doing, there's always some accuracy and precision associated with it that you should be aware of, right? As that is very critical and important to the instrument or to the experiment or to the deductions you're making from it. Okay, the last topic that is kind of interrelated to accuracy precision is significant digits. Right, so significant digits are essentially is defined as digits that are relevant and meaningful, right? But what I want you to take off of from is like significant digits, or the number of decimal places below or after the decimal point, or a number of digits you're using after decimal point, actually signifies the accuracy or precision of an instrument, right? So if you're thinking of a normal tape measure, right, that you're familiar with, right? So what is the kind of the measurement or accuracy or precision of that instrument, right? So you have the 1 inch mark, you have the half inch mark, you have a quarter inch mentioned, right? You will have below a quarter, you will have 1/8, and then depending on how accurate that is, you will have 1/16. Okay, so what happens if you have a measurement that is in between here? So if you're measuring something, right, and your measurement comes out to be in this gap in between, right? Because the accuracy of your measuring device is just goes up to 1/16 of an inch, right? You can't really say what is happening in between, right? You're making approximation. So the measurements accuracy that you're making can be only as accurate as 1/16 of an inch, right? And that is representative out here in the significant digits, right? So the main thing I want you to take out is not to have an arbitrary measurement, because it has, even the number of digits you put outside of this has an engineering or actual meaning associated with it. So essentially, when you are having 2 decimal places below this, you're saying the accuracy of whatever instrument that was used to measure the volume is only accurate about 0.01 liter. So any measurement below this, so let's say if you go ahead and your actual volume was 0.0001, this will only not be able to read 0.001 liters. This instrument, what was used, will not be able to read this, right? Because its precision or accuracy only goes up to 0.01. So it cannot make a decisive amount of what the value is below this quantity, right? That is going back to the same example, right? So if you had a point that was somewhere here, you cannot accurately say what this is because it's below the accuracy or precision error of that instrument. Okay, so as a result, you have to be mindful of this, right? So if you use a calculator, and if you do in 3, let's say 10 divided by 3, naturally the calculator will give you 3.3333, and this will go forever, right? But for the instrument that you're using, you might not have the 100 decimal places. You literally, if you're saying like you're trying to measure a distance and you're getting 3.333, and you keep on writing it to and say meters, you're essentially saying you can measure up to 1, 2, 3, 4, 5, 6, 7, 8, 9, literally 1 nanometer measurement, right? Your instrument is measure or accurate up to 1 nanometers, right? Which is not the case, right? or which might not be the case, right? So the number of digits you're using kind of talks about, or you're putting after decimal place, signifies the accuracy of the instrument. So that is the key thing I want you to take away from this. So you don't just arbitrarily use or put just any number of digits, right? Or any number of significant digits. So for here you have been given an example from the textbook. You have a volume which is 3.7. You have been given a density which is 0.845 kilograms per liter, right? And you have been asked to find the mass, right? So you're essentially doing volume multiplied by density, right? And you end up getting a 3.16875 kilograms, right? Okay, but now you see, even though you calculated mathematically this, the final answer that is displayed is only up to 2 decimal places, right? Because of the second fact that comes into play when you're using significant digits, is the fact that the final result will be only as precise as the least precise parameter in the problem that you're doing. Okay, so I always give the example of footballs and chains, right? So it is kind of interesting, right? So let's say if you have to measure this distance between these two lines, right? Now first you brought like a 1 foot ruler and you measured it up to this point. Okay, this 1 foot ruler had the accuracy of 1/16th of an inch, right? And you got this to be 1 feet. Okay, now you go ahead and okay, you have still so much distance left, and you somehow found, let's say, a super accurate laser guided measuring device which can give an accuracy about of 1/1000th of an inch, right? And this last measurement you were able to calculate it, and it came about to be let's say 0.0559, right? Okay, I'm trying to say 1, 2. Okay, let me just actually erase this. I think I made a mistake here. Okay, I will use a better word. So let's say the last bit that you're doing comes about to be 0.559 inches, or sorry, 0.559 feet, right? So essentially 1/1000th of an inch accuracy is there, right? So now if you are asked to measure the initial goal was what is the distance between these two red dots, right? So what you'll end up doing is adding this up, right? Now you have to be mindful that the initial measurement was using a ruler that was only 1/16th of an inch accurate, right? So even though the last bit you used to measure was using a very accurate instrument, the sum of these quantities will only be accurate or as accurate as, let me just use a different curve, as accurate as the least accurate measurement, right, which is this, right? So the precision or accuracy of that, the final, so if you say 1 feet, 1.559 feet, right, this accuracy of this final measurement is not going to be 1.559 feet because one of the measurements that you used only had 1/16th accuracy or precision, right? So your final sum of this will not be very accurate. So going back to this example of football and chains, so if you have seen if you watched football, you are aware like, oh, if you have a fourth down or third down measurement and you're very close to the first down marker, they bring out the chains, right? And I find it funny because to begin with, the location of, so let's say if this is your first down point, right? But the referee decided to place the ball out here. Okay. So, and then they bring out the chain and find like, oh, you are off by this many inches or fraction of inches, right? But the point is, the initial placement of the ball was made by referee by just eyeballing where it was, right? So he used a very imprecise technique to locate the initial location. So his initial measurement or accuracy of that measurement was very imprecise. So no matter what you do to the second part of it, right? You might bring even a laser guided measurement. You don't even have to bring chains. No matter how accurate of measurement you'll use here, it is not going to increase the total accuracy because of the first measurement you used, right? So when it comes to measurements, if you're using multiple measurements and adding them up or summing them up, the final measurement that you're using will be only as precise as the least precise measurement or parameter, right? So this goes back to the previous point or the problem that we used where they rounded off to the least precise measurement, right? Okay. So what does this significant digits signify or mean or represent, right? It is that, like we said, you're fairly confident on how precise the measurement is, right? So if you have put 2 decimal places of volume, you're saying you have fair confidence that it is the measurement you're getting up to 0.01 liters. Anything below this, you're not really confident because there's no way for you to measure, right? So if you say you have a volume of 3.746 liter, 3.75 liter, 3.753 liter, all of them actually just round out to be 3.75 liters, right? Because the fact that you are only confident or your instrument that you're using can only measure up to the first 2 decimal places, right? So finally, if for instance, if you're doing a problem and nothing is mentioned, the accepted engineering standard is 3 significant digits, which is essentially 2 decimal places, right? So if nothing is mentioned, you generally assume that you are accurate up to 2 decimal places, right? So you have to be mindful of when using significant digits or putting numbers in your problem. You don't want to signify that an instrument is more accurate or your measurement is more accurate than it truly is, right? So you can't just arbitrarily put a ton of decimal or digits after the decimal place because it's kind of misleading. Okay, so that kind of brings us to the end of this section. So next up would be, now that we went over some of the basics of a fluid and a solid and in between fluids, liquids and gases, just wanted to highlight certain applications that comes to mind, right? So I will have these links on the slides that you can look on, but I want to highlight a couple of them. So when it comes to fluid mechanics, right, the most obvious examples are, let's say, flow over a pipe, or aerodynamics, flow over flight or plane or cars, right? These are some of the obvious ones. So this is something I don't want to cover. It's obvious, right? I want to highlight some examples that are less obvious to you, right? So that some of them I have listed, but a couple of them which I will talk about is about weather forecasting, and when it comes to even microfluidics, right? Medicine delivery, drug delivery, or manufacturing of medicines or vaccines, right? Fluid mechanics still plays a big role in it, right? So when it comes to weather forecasting, right? So I have over here what you'll see is essentially this is taken from NOAA's website, right? These are any tropical storms or cyclones that have occurred around the North American continent from 1949, right? So more than 50-60 years, right, of span, right? What I want you to start thinking, if you look at these patterns and paths, so every wiggly line is essentially a path of a storm at some point, right? As a scientist or an engineer, I want you to try and see like, oh, can you find certain patterns or behavior that these storms have when it comes to USA. Let's start with just USA. Right. So specifically, right, so couple of things that come to our mind, right? If you look at it, right, if you see how they're originating, right, they're all originating from near the equator, right? You can see there's a bunch of always lines near the equator, right? So that is one thing that you can get out of this simply by observing it, right? The next thing and the most important thing I want you to get off is what is the deal with the storms on the eastern coast of US versus the west coast of US, right? So if you're thinking about Florida versus California, or thinking about New York versus Washington or Oregon, right? You can clearly see, right? You don't have to be any scientist or meteorologist to see that there is way more storms that hit the east coast than that hits the west coast, right? Literally, in the case of west coast, you can see there's like hardly, as especially Washington and Oregon and Northern California, there's hardly been a single storm that actually hit it, right? So what happens? What changed? Why is that bias towards east coast or west coast? Somehow earth or oceans like west coast and don't want to destroy it as much as east coast, right? What is resulting in this, right? So the root cause of this is essentially because of Earth's rotation, right? So this bias is caused because of how the Earth rotates, right? The Earth's rotation leads to how the ocean currents or air currents rotate and move, right? So when it comes to northern hemisphere, the air currents or ocean currents move in a clockwise direction because of the result of ocean currents, right? So if you're talking about clockwise direction, essentially the ocean is moving in this direction, right? Let me see if I can pick a better color so you guys can see. Right, so ocean is moving in this clockwise direction, right? Same thing, so that's in the Atlantic, but now same thing in the Pacific, right? The oceans are moving in this clockwise direction that is there. So what happens if it moves in the clockwise direction, right? So essentially, because the oceans are moving in a clockwise direction, what are you having? You're getting all these warm waters from the tropics or near the equator coming along the coast of Florida and rising up to New York, right? So essentially, because of this clockwise rotation, what you're essentially getting is this warm waters coming up towards the east coast, right? Because of the clockwise rotation. Now, if you look at the Pacific side or the west coast side, because of this clockwise rotation, now what you're getting is all the cold waters from the Arctic regions are actually being brought down here, right? So as a result, you have cold waters on the west coast. So if you have ever been to a beach in west coast and a beach in east coast, and if you have ever dipped your feet or touched it, the one main difference you'll see, naturally it has to be similar latitudes, right, is the west coast waters are always very cold. Even if you go all the way to San Diego, even in summers, you'll see that the waters are considerably cooler and colder compared to the east coast waters, right? And this difference in temperature because of the motion of the ocean currents is the root cause of the storm, right? So for a storm like a hurricane or a tropical storm to be sustained, it needs warm waters, right? So as a result, the more warm waters is exposed to, the more strength the storm gains, and as a result, most of it comes and hits the east coast. While you can see on the Pacific side, there is still storms originating near the equator, but by the time it comes to California, already it is hitting cooler water, so it's not sustaining, or it does not have enough energy to sustain the storm, so it dies off. So there's none, as a result, there's no storms hitting it, right? So this whole rotation, or how the ocean currents move, how the storm moves, are all actually, when you think about our weather forecasting, it all actually falls under fluid mechanics, right? Air, water, weather patterns, that you have water, rain, clouds, are all nothing but fluids, right? So what students don't realize is weather forecasting or meteorology actually is a subpart of fluid mechanics, right? So with that being said, another example would be kind of slightly different from the traditional example, is related to vaccine development, right? So now with COVID we just passing and recovering from a pandemic, we all heard about the vaccine and how it's developed, right? So the novelty or the ingenuity was about developing this mRNA vaccine, right? So mRNA itself has been something that has been known for a while, right? It is not that it was developed or that technology was not something that came up while during COVID, right? mRNA itself has been for a while. The issue was mRNA by itself is very unstable. So if you create a vaccine, it will not last for too long, right? So it does not have as long of a shelf life. So how do you make a vaccine that will have a long shelf life, that it can be transported to different parts of the country or even the globe, and it still stays, so it will take days and months, and it can still stay stable so that it can be administered to needed patients, right? So the main discovery or ingenuity came in figuring out that if you coat mRNA with these lipids, these tiny particles, right, the lipids itself are stable, and that keeps the mRNA stable or protected in some sense, right? But the point is, how do you do this in a very successful high production rate manner, right? You cannot expect to pick one RNA, which is kind of a form of similar to a DNA, individually and coated with these tiny particles. These are literally molecule size, right? Or cell size, right? So how do you do this without coming up with a very time-consuming procedure or manufacturing technique, right? So this is where one of the main engineering breakthroughs or discovery happened for them, right? Naturally, is the actual mechanics is proprietary, we'll never know, but essentially what they had is a series of pumps. So essentially you can think of it as you have two tanks. One tank has lipids in it and the other tank has mRNA in it, right? So with these two tanks, you have very precise pumps that brings this fluid from containing lipids and a fluid containing mRNA and combines them together. And when I'm saying precise, essentially the precision of these pumps have microliter or nanoliter precision, right? So by properly mixing or determining the rate of flow of lipids and mRNA that get combined into a common flow or a common duct or a pipe, So essentially, or controlling that, they were able to figure out a process in which you can coat this mRNA vaccine or mRNA molecule with lipids, right? Just by controlling these pumps and mixing two liquids together. But the whole this neat thing is this was done in a very precise and controlled mixing manner, right? So without having this kind of allowed them to increase the production rate, right? So otherwise, if you're thinking of physically doing it, if it takes hours to create one of these molecules or a right, so it will take forever to kind of to produce or generate significant amount of vaccines that can be delivered, right? So this whole pump system that they developed kind of was one of the major breakthroughs that allowed for so fast vaccine production, right? So these are just to highlight both weather forecasting and this vaccine example is to highlight is fluid mechanics goes way beyond just some of the traditional things that you're used to seeing and you experience, right? Okay, next we'll be covering two important concepts in engineering, which is dimensions and units. So I want to remind or specify that this is nothing specific to fluid mechanics. It's a general engineering concept which you can use in different aspects, and probably some of the things we are talking about you've already heard of. So the first thing is called dimensions, right? So when you're talking about dimension, any physical quantity can be characterized as dimensions. So one of the dimensions you can think of is length. The other example of a dimension is time. Another can be mass, right? And so on and so forth. Now, when you assign units to this magnitude of respective to a specific dimensions, then it starts making more sense, right? So the magnitudes assigned to dimensions are called units, essentially, right? So the main thing to bring it out here was to make sure to emphasize that whenever you are solving any problem, you have to be very, very careful on the units. So you have to make sure you're using consistent units throughout, right? This might seem trivial, but they have real life consequences, right? So the two common unit system is the metric system and the English system, right? So it doesn't matter which one you follow, you just have to be consistent throughout your problem you're solving, right? So I'm pretty sure you might have heard this, but you don't want to be this person, right? So I think it was back in 1999 where NASA lost a Mars orbiter, right? And the whole reason for this loss was that NASA uses SI units, but they had outsourced some of the work to Lockheed Martin, and one of the persons, and I guess it's a team of persons, and Lockheed Martin uses the English system, right, versus the SI system, right? And they never made the proper conversion or made the units consistent. Naturally, that led to miscalculations, like it's saying like everybody's using, instead of saying 100 meters, he said 100 feet, right? There's a big issue with that, right? And that completely led to a project loss, right, of 125 million, and that's just the cost of the orbiter, right? If you think about the cost associated with other things, just the launch and the workmen and the workforce, that is way higher than this $125 million, right? So this looks like a trivial issue that every professor raises, but it has real life consequences, right? So make sure that whenever you're using units, you're using consistent units, right? That is something I will be very on top of, right? So whenever you're writing, if you're doing a homework or exam problems, I will always check if you're using consistent units or you're presenting your answer in units, right? So if I'm asking you force, you are writing in newtons rather than you have a wrong unit of Newton meter, right? That's a wrong answer. And this is just to emphasize and making sure you get into this habit of using consistent unit. The reason I brought out dimensions was dimensions can be used for a very important consistency check throughout the problem. You'll see me use this multiple times, right? So when you're talking about dimensions, there are something called as the primary dimensions. Right, so primary dimensions are dimensions essentially, for instance, like length, mass, time, temperature, right? If you're thinking about electricity, then it comes to current, right? And they're called as such because any dimension on any quantity or any variable that you can think of can be formed using these primary dimensions. There are more for different quantities. These are some of the key ones that you'll be encountering at least in this class, right? So for instance, if you're thinking about, let's define a new variable, velocity, right? Velocity is nothing but length over time. Right, if you're talking about a new dimension or a variable, say density, right? Density is nothing but mass over volume, which is length cube, right? Okay, so essentially primary dimension are dimensions which is elementary, and any other quantity or variable can be formed using these primary dimensions, right? So where it comes in handy is if you look at any equation, it can be algebraic, differential equation, right? Any equation that you have to have consistent dimensions in order to do a mathematical operation or to sum them up. So let me give an example. For instance, if you're saying, if you have an equation A plus B is equal to C, right? Now if A has dimensions of mass, then B should also have a dimension of mass, and same with C. It cannot have a dimension of, say, C cannot end up having a dimension velocity. That is inconsistent, right? So essentially any quantity that are summed up in an algebraic or differential equation, all of those, each variable or each summed quantity should have the same dimension, right? So what this can be used for is to find units or dimensions of a relationship, or to do consistency checks if you're deriving an equation, right? So, or you have you kind of remember, but you're not 100% sure of what the dimension is exactly, right? So let me give an example here. So let's say if you have a relation where A times B is equal to C, right? And the unit of C is, or dimension of C is mass per length cube times time. Okay, and you somehow know that, okay, A has a unit of mass. But you don't really remember or know what the unit of B is or the dimensions of B is, right? But by using this fact that the dimension of every quantity or summed quantity has to be same, you know that A times B should have the same dimension as C, right? So that will give us the fact that since A times B has to have the same dimension as C, which is m divided by L cube over T, that means the dimension of B is nothing but times by L cube. Now you can see that these two dimensions are consistent, right? So essentially you're not ending up adding apples plus oranges. That's kind of the goal here, right? So something that this comes in really handy, and I'll be using it throughout the course, is this consistency in dimensions, which there's a chapter which we'll come across later in the course, right? But this is an easy way to check consistency of your problems that you're solving, and also consistency of the derivations, right? You cannot have a situation where your dimensions on the left hand side and the right hand side are different, or the units are different, right? And that's all related to the consistency check. So that's the key takeaway I want you guys to get from this slide about dimensions and units, right? So you need to have consistent units, and you need to have a consistency in dimensions. The next topic is just about modeling in engineering in general, right? And there's a systematic way of approaching problems in engineering, right? And I just have this slide to emphasize that I have a specific format that I request or need students to follow whenever they're doing mathematical based problems for homeworks or exams in my class, right? And so on D2L you will find a format of solving this problem, right? So couple of things here, right? So in the beginning, so I'll just highlight some of the key things, right? Before you solve the problem, I need to see some of these quantities, and it is all based off this principle of modeling in engineering, right? So one is I need to see a schematic, right? So essentially you can think of a schematic as some kind of free body diagram, right? So essentially a schematic is a rough diagram. It doesn't have to be perfect lines. It can be a rough sketch, but it needs to quantify what is being asked to solve and describe what is given to you, right? So it's a good habit to develop to draw schematics for problems. So if it's a word problem that is given, can you draw a corresponding schematic, right? It's like saying if your car is stuck and car broke down and you're trying to figure out a problem, you can text your friend and just try to describe it in words what the problem is, or you can actually take pictures and show it to them, right? So one is easier and better to communicate than the other, right? Pictures help, and if you make marks or pointers in the pictures, that's even better, right? So schematic you can think of in that sense. So for every problem that you're given, I need to see a schematic, okay? The next thing is I need to know, you need to list out, you don't need to write in descriptive form, but you need to list out all the quantities or variables that are given to you in the problem. The next thing is you need to list out what are the quantities that have been asked in that problem. So all the things that have been asked to find. Once you have done these three, the next thing that is less common or less you're not as much used to doing is that I want to see assumptions, right? And this is mainly to make sure you get into the habit of identifying various assumptions that goes into a problem. no matter what problem you're solving, how simple or complex, you're always making some kind of assumptions. Because no problem or no equation or no relation is true for every given scenario in the whole universe, right? So you're making some kind of assumptions, right? And this is a very important issue, right? So I always in class give the example of, I believe it was Challenger, the space shuttle mission Challenger, which blew up like 70 seconds into the flight, right? For those students who don't know the cause of it, the whole reason that it blew up was an O-ring failed, right? You have probably seen an O-ring if you have ever dealt with pipes or any kind of gaskets, or even water bottles sometimes have it, right? Essentially, it's just a thin rubber tube to seal the gap between two connecting objects, right? So no water leaks out or things on that line, right? But what's the deal with rubber? What happens to rubber if it's exposed to very cold temperature, right? A rubber, the reason you use rubber is because it's a bit flexible, it squeezes into gaps, and you can compress and make it, it's a bit ductile as well, right? But when you reduce the temperatures or expose it to very low temperatures, the rubber is not as malleable or flexible anymore. It becomes brittle and rigid, right? So you can actually just snap or break a rubber O-ring if you expose it to freezing temperatures, right? So essentially, in the case of Challenger, in the solid rocket booster, there was the O-ring gasket or rubber gasket that failed. And the reason for its failure was the space shuttle, because of delays, was on the launch pad for other delay reason, and was the initial launch window was missed, so they had to wait for the next launch window, and it was stuck on the launch pad exposed in Florida. And during that time, a cold front had come in, where the temperatures had dropped way below the standard nominal temperatures that you expect in Florida, right? So it was close to freezing temperatures. And some engineers knew about this, and they pointed it out. But a decision was made that this was an acceptable risk or acceptable issue, and the failure there would not be any specific failures. But lo and behold, because they kind of ignored this assumption that, the fact that a rubber's properties changes, or ductility or malleability changes outside of a temperature region, so it's no longer as flexible as what is designed to be, and that can have disastrous effects. That assumption was no longer true, that it is going to have those properties, right? Because it went outside of that limiting or design constraint. And naturally, a rocket is subject to a lot of vibrations and motion, and as a result, since the rubber was not enough ductile and malleable, the O-ring failed, which led to the main cause of failure and destruction and loss of life of astronauts, right? So that's one of the things I want you guys is to develop and want to emphasize. Is any problem that you're looking at, you're always making assumptions. Sometimes it will be explicit in the problem, but even implicitly there are always assumptions. So I want to kind of encourage you guys to kind of think a few minutes about all the assumptions that you're making. It's a good habit to develop, especially if you're designing or developing anything, right? You should always be aware of that. So as a result, I always would want to see assumptions, right? Once you have assumptions, I want to see finally the equations or the laws, if you're using conservation of mass law or conservation of momentum, that you're using in the problem. Only once you have done all of these 5 would I want to see finally you start solving your math problem, right? Essentially, to emphasize, this is a systematic way to set up the problem, right? And I want you to force you to kind of students to follow and get into the habit of using this problem, right? So as a result, there are points associated with this, right? So if you miss one of these 5 items or things, you will lose points in your homeworks and exams, right? But on the flip side, you can get free points by just properly stating your problem in this given format, right? So again, I just wanted to emphasize this, and you'll see it when your homeworks and exams are graded, right? So please make sure that you're following this format. I have a more cleaner version of this written in the uploaded on D2L of the formats to follow, some exceptions you can make for exams, and so on and so forth. Some of the forces and stresses that are experienced in a fluid element, right? And you'll be seeing that some of these forces you are familiar with, right? So any forces that forms or a fluid experiences, no matter the most complex forces for the most complex fluid flow or the simplest forces, right? They might be called different terminologies or names, but they are all originates or all a result of just 2 fundamental forces, right? Right, or stresses, right? So first thing I want to go is the kind of refresh your memory on what's the difference between a stress and a force, right? You will be coming across this multiple times in this fluids course, so it's kind of just want to refresh it, right? So when you're talking about stress is nothing but force per unit area, right? So what are the difference between a surface force and a body force? I'm not sure if you have heard of these terminologies before, right? Probably you have, but I wanted to refresh your memory if you've forgotten, right? So now that we have talked about stress, if we go into forces, you can subdivide these forces into surface force and body force, right? So surface forces are essentially, if you want to go over here, right, surface forces are essentially forces like pressure. Let me just change my pen quickly. So example of surface forces would be pressure, right? Or stress. Right? On the other hand, example of body forces would be forces such as gravitational force or gravity, right? Or electromagnetic force. Right. So if you can probably guess from the name itself, right? Essentially, surface forces are forces that acts on the surface of a system. If you're talking about a body, right? If you're applying pressure, you're applying pressure just on the surface, right? So if you have an object or a system that you're studying, if you're talking about pressure, you're talking about forces acting just on this surface that is there, right? So that is pressure for you. Similar with shear stress or other stresses, right? But when you're talking about body forces, you're talking, and a best example is gravity or gravitational, right? When you're talking about gravitational forces, you're saying that the gravitational force is called body force because it acts on not just the surface, but every atom that constitutes or makes up that system, right? So a gravitational force will act on each and every molecule that is out there, right? And hence it is called a body force, while pressure or stress is called a surface force or shear stress. Okay, so when it comes to so stresses, right, or forces, you can divide the forces or stresses into 2 components, right? One that is acting parallel to the surface of interest and one that is acting normal to it, right? So a normal stress is nothing but the normal component of force acting on a surface per unit area, right? And when you're talking about tangential stress, an example of tangential stress, or the more common name of the tangential stress, is shear stress, right? Okay, so you'll always have two components of force acting on an object, that is a normal force and a tangential force. Tangential force or stresses corresponding to tangential force are called shear stresses, while the stress corresponding to the normal force are called normal stress, right? Okay, so now given a specific situation, you might have one of these forces might be zero. So it might be that you just have a normal force component, you don't have a shear force component. Or it might be the other way around, you have a shear force component, you don't have a normal force component. But any force or any complex situation that you can think of, right, are always a force constituted or made up of these two forces, right, a normal force and a tangential or shear force. Right. So an example or a common example of a normal stress associated normal force is pressure, right? So I'm hoping everybody have heard of this term pressure, right? So when you talk about pressure essentially is a normal stress of a fluid which is stationary. So that is something to be very mindful of, right? So that the fluid is at rest. So when the fluid is stationary or at rest, then the normal stress will equal to pressure, right? But if the fluid is moving, this fact of normal stress might not necessarily be equal to pressure in the case of a fluid moving, right? So the fact that a normal stress is pressure, or pressure is an example of normal stress, is only true if the fluid is stationary or at rest. So that is something that you need to be very mindful of or aware of. Okay, so that is one of the things that I want you guys to take away from this slide. The next thing I want to do is, when a fluid is at completely stationary or at rest, you will have zero shear stress. So there is no tangential stress in a fluid if it is completely stationary, and we'll see this as we go along through the course, right? So few things to take away from this slide, right? So the first is you have normal and a tangential component of stresses and forces. The tangential component is also called as the shear stress, right, which is you're probably familiar with. When it comes to normal stress, an example of normal stress is pressure, but that is only true when fluid is at rest, right? And finally, if the fluid is stationary or not moving, you will have zero stress, right? So these are just basic concepts that I wanted to refresh. Probably you already are aware of, if not, introduce you to, that is associated with fluid, right? And last but not least, I guess I've forgotten this, that stress is force per unit area, something that we'll need over the course, multiple times throughout the course. Okay, now that we have just gone over basic terminology of forces acting on an object or a system, specifically to fluid, let's kind of refresh your memory on the basic differences of a solid and a fluid, right? So first thing I want to make sure that you guys know, because this is something often students confuse of, and people are not, when you're talking about a fluid, both liquid and gas is a type of fluid, right? A fluid means both liquid and gas. So it's not just liquid and it's not just gas, right? Both fall under fluids, right? right? So what is the basic difference between a solid and a fluid, right? The first thing, and this is the key thing that defines if an object is a solid and a fluid, right? So if you can think of a solid, right? So if you have a solid rubber like this brown object, right? If you make sure that the bottom surface is stationary and then you provide a tangential shear force on the top surface, right? You can see that it will deform the rubber, right? So, but for a finite amount of force that you apply, right? So, finite amount of force that you apply, this deformation of shear deformation would be finite, right? So that is the main thing about a solid, right? So a solid can resist any applied shear force by deforming, right? So that's kind of what this is saying. And so the other way of what I said is if you apply a shear force, the deformation, what you get is a finite deformation when it comes to solids. On the other hand, in the case of fluid, right, as if you apply a finite amount of force, right, so it's the same finite amount of force you apply, what you'll see is this fluid will continuously deform, right? So there is no longer a finite deformation, right? It is going to be a continuous deformation, right? So as long as, so let me just highlight this part. Okay, so as long as there's a force applied on a fluid, the fluid will constantly keep on deforming. No matter how small the force is, how big the force is, right? Right, the deformation of a fluid will continuously happen, right? So that is kind of the main distinction between a fluid and a solid, right? And something that I mentioned previously in the first lecture, right? This whole idea, right, or this notion or this fact that a fluid is continuously deforming forms the source of biggest headache for students, right? Because it is continuously deforming, you cannot look at fluids often in the same way as you can look at solids. So you cannot study them exactly the same way. And this change of perspective as a result of it is kind of makes it harder, right? The second thing which makes it harder to study fluid mechanics is this fact that now that I'm saying this, the fluid is continuously deforming, right? I can bet you for most students this is very hard to perceive, right? When I talk to you about a solid having a finite deformation, you can, if you bring a rubber or a rubber band or an object, you can know that, if you pull on it or push on it, right, there is a finite deformation, right? So it is very tangible and easy to see. But when it comes to the fact of a liquid or a gas, and if I say that it is continuously deforming, it is very hard for students to perceive, right? Think about it as even you moving around or walking in the room, right? Or moving your hands as you're sitting and watching this lecture, you're technically constantly deforming the air around you, right? But this is something very hard to perceive. And for this, I kind of have a video in the next slide, and hopefully this will help you understand that better. Right. So as a result of this finite deformation in solids and continuous deformation in fluids, there are two main differences that happens, right? So if you think the strain is essentially the extent of deformation, right? If you remember from solid mechanics, it's, if you think about linear strain, essentially linear strain is nothing but delta L, that is change in length over the original length of the object, right? If you're talking about shear strain, you're talking about change in angle, right, of the system that you're looking at. Okay, so solid mechanics, hopefully you remember that stress is proportional to strain, right? But now the challenge comes in fluids, right? You don't have a finite deformation anymore, right? So let's say if you look at the fluid, how much it has deformed in 1 second, you'll get a certain angle to it, right? But 2 seconds later, if you look at it, since it's continuously deforming, this angle would have changed from, let's say, 5 degrees to 20 degrees, right? Now, 5 more seconds later, it would have changed from 10 degrees to 30 degrees, right? So, because a fluid is constantly deforming, you cannot define a strain for a fluid, right? So it means for both liquids and gases. So what we do instead is we define something called as the strain rate, right? So when you're talking about a rate, right, essentially it is meaning the time rate of change of a quantity, right? So how much strain you have let me just write this. How much strain you have per unit time or per unit interval of time, right? So that's what strain rate means, right? So let's talk about, maybe you've heard of rate as volumetric flow rate, right? Those are like essentially when you're talking about rate of change of something, right? So when you're talking about strain rate, you're talking about how much strain you're having per unit time. So when you're dealing with fluids, you talk about stress being proportional to strain rate, right? So this is one of the key takeaways for you, is when dealing with fluids, you're talking about stress being proportional to strain rate and not strain, because fluid is continuously deforming, right? So these are the two things that you need to take away from this slide, right? So this is what defines if an object that you're studying is a fluid or a solid, right? If it is continuously deforming under shear, then it's a fluid. If it's not continuously deforming, then it's a solid. So now that we have that, right, the next distinction I want you to make is between what's the distinction between a solid, liquid, and gas. So in a fluid, what's the distinction between liquid and gas, right? Some of things of these you are already aware of, and it's pretty obvious, right? So when it comes to solids, right, if you think about first with the molecular patterns or arrangements of it, right? So when it comes to solids, the molecules are arranged in a specific pattern, right? And it's often repeated throughout, right? So probably you've heard of FCC lattice structure, BCC lattice structure, right? When it comes to liquids, molecules are no longer specifically arranged in a specific pattern. They are allowed, they can rotate and move around and translate freely, right? And when it comes to gases, there is literally no order at all, right? It can literally bounce around and move around anywhere, right? And this is as a result of the interatomic forces, right? So if we talk about interatomic forces, when it comes to solid, it is you have the strongest interatomic forces. When it comes to liquids, on the other hand, right, it is relatively less, right? So it's strong, it's less, the strength is less than solids, but it's still stronger than gases, right? And of the three, the weakest interatomic forces are of that of gas, right? So the last 2 points you are probably well aware of, right? So the next point is something I want to highlight that is probably less familiar with. So when you talk about a volume of a solid, right, it often stays constant, right? So that is very intuitive. But when you talk about liquid and gas, things are slightly different, right? When you're talking about volume of a liquid stays relatively constant, right? And this I want you to, and I will emphasize or clarify this. When you compare this with volume of gas, which actually varies depending on the size of a container, right? So for instance, if you think about if you put, let's say, if you have a hydrogen or helium balloon, you or a gas balloon that you bought off a store or for a birthday, right? If you release the gases, right, what is the volume it will occupy, right? If you give enough time, it will fill up the whole room that you have, right? If the whole room has leaks, it will actually fill up whatever space it has contained in, right? But initially, till you did not release it, it actually filled up the whole balloon, right? So essentially, when it comes to the volume, right, the main distinction that happens is between a liquid and gas, right, and which is less intuitive. When it comes to gas, it will fill up literally entire volume that is available to it, right? So it fills up or occupies the container fully, right? This is not the case when you're dealing with liquids, right? When you're dealing with liquids, it does not necessarily fill up the entire container, right? So this might seem counterintuitive a bit to some, right? So let's say, and the best way to give an example of this is by looking at limiting cases, right? So let's say if you have a container or a glass here, right? And let's say it was a closed container, all right? So now if I say, if this was a 1 gallon container, but I only poured in this 0.5 ounces of water in it, right? What will happen, right? So in this case, right, naturally it's not going to fill up the whole container. It will only fill up a part of that container, right? So even though the liquid takes the shape of the container, it only does so partially, right? It's not perfectly taking the shape of the container, right? So if you don't put enough volume of the liquid, it will only partially take the shape of the container. It does not occupy the whole volume. And that's the main distinction between a liquid and a gas, right? For instance, if you had the same 1 gallon of container, and if you put 0.5 ounces of helium in it, eventually this 0.5 ounce of helium will completely expand and spread and occupy this whole space, right? That is not the case with water or liquids, right? And that's because of how the interatomic potentials or interatomic forces work, right? So it takes the shapes of the container, but with a free surface, right? So if there is a free surface. Now naturally, if you have enough water, so if you have 1 gallon of water, then it will take the complete shape of the container, right? So there's a conditionality to it, right? So it's not always the case that liquids fill up the whole container, right? It is conditional on that. But for when it comes to gases, it will always fill up the full container, or occupies the volume of the container, or take the shape of the container. So just wanted to highlight this because this is something that you guys are not probably familiar with when it comes to a liquid and a gas. Okay. When it comes to mechanics, right? Mechanics essentially is the science that deals with both stationary and moving objects, which is under influence of some kind of force, right? So this is true for both solid mechanics and in fluid mechanics, right? The main difference between, as you might guess, in solid mechanics you're dealing with the motion, or if the body is stationary, of solids, when it comes to fluid mechanics you're dealing with fluids, right? So more of the formal definition is the study and analysis of matter through the conservation laws of physics, right? Which means the conservation law of mass, momentum, and energy, right? So when you talk about mechanics or forces acting on stationary and moving objects, this is true for all different length scales, right? So I just wanted to bring to your attention the different length scales that sometimes you might even overlook, right? All of this understanding or study of any of these objects or subjects all fall under mechanics, right? So if you start from the smallest length scale, let's start with molecular or atomic scales, right? Examples of this would be if you're talking about forces on electrons, intermolecular forces between, let's say, hydrogen and oxygen atoms in a water molecule, right? Forces exerted during processes like nuclear fusion and fission, right? All of this forms the basis of mechanics, right? All of them fall under mechanics. If we now move on from molecular scale to, let's say, micrometer scale. So if you're talking about drug delivery, when you're talking about new vaccines that were developed for COVID, let's say mRNA and lipids being bonded together to create the Pfizer vaccine, or you're talking about electronic cooling. So if you have a microchip or microprocessors, it gets super hot, right? And it would amaze you, or probably you have not heard that the energy density or the heat density, that is the energy per unit area in a microprocessor, can actually go up to the energy density of a sun, right? So that is super hot, right? But it happens in a very small area. So in electronics, cooling is a very important part, right? So how does the air or liquid or convection cooling or liquid cooling affects the temperature, or you can maintain the temperature at an optimum level to get the optimal performance, right? So those studies also kind of fall under mechanics, right? When you go from micrometer scale to now few inches scale, right? So think about baseball, right? Something that we'll be covering when we do external flows is what's the deal. If you're a baseball fan, probably you've heard of a curveball, right? So how do you generate a curveball, right? That is actually a result of aerodynamic forces because of rotation of the ball, right? If you have seen, right, one of the main criteria of getting a ball to curve is that you have to provide enough rotations. Enough rotations provides enough asymmetry in the aerodynamic forces that were providing a side lift, which is leading to curveball. There's the same principle that goes into curving a soccer ball, right? If you're bending a soccer ball, if you're more into a soccer fan, right? But these also, the principle of it kind of falls under the category, or the study of it falls under the category of mechanics, right? Something which we'll eventually be covering later in this course. When you move from few inches to a couple of feet, right? Let's say as simple as the chair you're sitting, right? If you're designing or developing a chair, you have to account for the forces that it will be acting on it, if it can hold a certain weight, right? Or simple as rotation of tires of your car, right? In your car, right? Anything that you can think about are always subject to some kind of force, no matter what, if it's stationary or moving, right? So in theory, if you're studying any of these objects, that study falls under the in general term of science called mechanics, right? Let's say if you go from a couple of feet to hundreds of feet, right? So now if you're going to hundreds feet and you're building ships, right? So in this case, ships are few hundreds of feet, right? So if you're trying to design and build a ship, that's an example of mechanics in hundreds of feet, right? Or let's say if you're designing a building, the next skyscraper, right? If you're a civil engineer designing, or you're an architect designing, you're still accounting for loads on the beams, loads on different stresses and joints, right? Those all kind of fall under mechanics, right? Now, when you go from hundreds of feet to, let's say, hundreds of miles, right? Can you think of examples for an object that is under force in hundreds of miles, right? So one example that people can is probably you are thinking or might have not thought of is plate tectonics, right? In theory, the surface of Earth is never perfectly stationary. It's moving very slowly, right? So essentially, when you're thinking about earthquakes that are happening, right, that is plates moving against each other or getting lifted up, right? Those plates are subject to forces which are also, so if you're studying the Earth's surface or plate tectonics, that's also an example of mechanics, right? Now, if you go to weather patterns, right, if you're talking about forecasting weather, those also actually fall under mechanics, because the way the clouds move, the way the ocean currents move, or the air currents move, are all subjected to forces which all hence fall under mechanics, right? Now, if you go to light years, right, even then you have gravitational forces, right, of interplanetary gravitational forces, right? Think about the comet's orbit, the Earth's orbit around the sun, the motion of galaxies, right, the motion of the Milky Way, right? Those are all subjected to some kind of gravitational forces of cumulative objects in the sky. Hence, even if you're studying an interplanetary motion or interplanetary forces, it's all falls under mechanics, right? So in general, mechanics is a very, very broad topic. So now, as we said, right, we already talked about mechanics and said that mechanics is a study of forces acting on bodies that are both stationary and moving, right? So now we are focusing on the two terms of a stationary object and a moving object. So as mechanics can be subdivided broadly into study of objects that are stationary, which essentially forms statics, and any study of objects that are in motion that forms under dynamics, right? So that should be straightforward, something that you have heard and you know about, right? But I want to emphasize this fact, right? An object is stationary or moving, and that will determine or is determined by the fact of the frame of reference, right? So this frame of reference in which you're looking at. So for example, to highlight this, right? So if I tell you, if you're studying your chair, what will you call it? Studying forces on a chair that is sitting. And let's say forces subjected on it by a person sitting on it, right? Will you call it as a stationary object, or will you call it as a moving object? So in terms of mechanics, will it fall under statics or dynamics, right? So intuitively, the first thing that will come to your mind would be, well, it's a chair, right? It's not going anywhere, so it is stationary, right? So it falls under statics. And that is true, right? But that is true from the perspective of what you're thinking of most of the time, that you are on Earth and you're looking at it, or you are in the same room as the chair and you're studying the chair, right? But now if I tell you, if you're looking at the chair or you're observing and studying a chair from the International Space Station, right? So from your perspective, that point, Earth is rotating. So as an astronaut, from your perspective, the chair, as a result, is also moving, right? So chair is no longer stationary. So it's moving, right? So that's why when you're talking about statics and mechanics, or object being stationary or being moving, you have to be very particular about this, right? So you have to be very particular about which frame of reference are you looking at, right? What frame of reference are you studying or observing, right? So let's say if I give you the example of, let's say, a cup holder in your car, right? So what will you call the cup holder? Is it stationary or moving, right? If you're studying the cup holder, right? Well, it depends, right? It depends on what you're looking or what perspective you're looking at, right? If the car is not moving, right, and if you are a neutral observer from either sitting inside the car or even outside the car, since the car is not moving, the cup holder is not moving, right? Now, what happens if the car is moving, right? In that case, will it still be a stationary cup holder or moving cup holder, right? Again, it will depend. It will depend on the frame of reference, from what perspective or point of view you're looking at it, right? So let's say if you're looking at the cup holder from a person driving in the car, right? So while the car is moving around, from your perspective as a person inside the car, the cup holder is stationary. It is not moving, right? So then it falls under statics. But now if on the other hand, if there was your friend who was looking at from outside the car at the same cup holder at the same time, from his perspective, the cup holder is moving because the car is moving, right? So in that case, for his, the cup holder is no longer a stationary object, it's a moving object. So it will fall under dynamics, right? Similarly, you can make this argument for any object or any system that you're studying, right? So the one thing that I want to highlight and emphasize in this is the fact that anytime you are looking at an object, if I ask you if it's stationary or moving, you have to think from what perspective you've been asked to look at, right? Is it from the frame of reference of the object, or is the frame of reference from outside the object, and with respect to that it is moving or not moving, right? So that is the key point that I want to take away from this slide, right? So when you're thinking about an object is stationary or moving, please make sure to check on the respect of from which respect of the reference frame, or which reference frame you're looking at that problem. Okay. So now that you have understood or have the basic understanding of statics and dynamics, which probably you're familiar with already in your previous classes on solid mechanics, next, when it comes to fluid mechanics, as you have guessed, it is nothing but the mechanics or the science of dealing with the behaviors of fluids, right? So is the fluid moving? Is the fluid stationary? Anything that has to deal with fluids falls under fluid mechanics. So fluid mechanics is a very broad term. Okay, so subcategories or sub-terminologies that are often used for specific problems under fluid mechanics are hydrodynamics, right? So when you hear hydro, the word hydro, what comes to your mind, right? Hydro generally refers to water, right? So any study of motion of fluids that is specifically related to water falls under hydrodynamics, right? But it is more often, water you can think of as essentially a liquid, right? So more often it is more broadly used to refer to not just liquid water, but any study of any liquids itself, right? So that's what it means when you're talking about incompressible, right? So liquids are generally assumed to be incompressible, which means you cannot compress or change its density, right? So essentially hydrodynamics is not just the study of water, which is what the literal meaning is, but is more broadly referred to a study of just liquids in general, right? When it comes to gas dynamics, right, as you can see, the gas would mean the name would suggest that it is essentially no longer, it refers to the study of gases, right? So it can be study of air moving around, or if you're, let's say, designing a gas turbine engine, right? So study of fumes or different gases going through the combustion chamber of that gas engine, right? So those all will come under gas dynamics in general, right? When it comes to aerodynamics, right, that is specifically, you can think of it as a subcategory of gas dynamics. It's similar to gas dynamics, but when you're talking about aerodynamics, you're specifically talking about flow of air around objects, right? So that's why when you talk about, designing the aerodynamics of a car, of a plane, you're always mostly referring to air, right? So that's just a subcategory. Similarly, there are other various subcategories in the field of fluid mechanics. So you have meteorology, you have oceanography, you have hydrology, which deals with different specific topics of fluids.